Hi. In this video, I'll introduce you to some of the introductory topics regarding earthquakes. Make sure as you watch, you're paying attention and you're taking good notes. As always, come see me if you have any questions. Let's dive in by reviewing some of what you probably already know about earthquakes. An earthquake is a shaking of the Earth's crust that results from a release of energy. Now, as you've already seen in class, most earthquakes occur along the plate boundaries. That's because as two plates rub up against each other, that causes friction, it causes stresses and torques on the crust that builds up energy until a point in which the energy can't be stored anymore and it gets released. Kind of like stretching a rubber band until the point where it just can't stress anymore and it either breaks or springs back. Most earthquakes occur at something called a fault, which is the crack in the Earth's crust, many of which are at plate boundaries, although there can be some faults within a plate. There's some other vocabulary we need to describe just to make sure that we're all on the same page with some of the vocabulary words. So the term focus refers to the earthquake's origin that includes not only the latitude and the longitude, but also the depth. Whereas epicenter refers to the position on the Earth's crust directly above the focus. So in other words, latitude and longitude without the depth. When we study earthquakes, there are really two main lenses we want to study them through. Of course, we want to talk about how they're hazards, dangers to life and property, and we'll talk about all the different ways that is. But first, I want to talk about how we can study earthquakes and learn about them, and not only about them, but about the Earth. And the primary way that we do that is through seismic waves. So a seismic wave is the wave of energy that flows outward from the source of the energy. You can think of them as vibrations through the ground, almost like if you had some jello and you gave it a little flick, and it would go out in all directions. So there are three types of waves, and you have a chart in your notes, but my bullet points will cover all of the same information. So the first item in your chart is where they start from. Our first two types of wave are classified as body waves because they start from the focus, meaning they start from the depth of the earthquake, and they go through all of the surface of they go through all of the body of the Earth, or a good portion of it for some of them. Conversely, surface waves, as their name implies, travel along only the surface of the ground. So they would start at the epicenter. So the first type of wave that we'll talk about, and the first one to get there, is called a primary wave, also known as a P wave. I'll show you how you could try to draw this in a second, but it might be worth your time to write the words for how it moves, and that is that it stretches and compresses the Earth. I'll show you some more about that in a second. And of the three types of waves, it's by far the least destructive, and it also gets there the fastest. It travels the fastest, so like I said, it gets there first. It's also really important to note that of the three types of waves, this is the only one that can travel through liquids, solids, and gases. That becomes really important when it comes to studying the interior of the Earth. So, the drawing, like I said, is kind of challenging to show. It's just stretching and compressing. And so if you look at this graph, you can see that the distance between the lines, which should be equidistant, aren't. The best way to draw it, I think, is something like this, because that other diagram is a little bit tough to show. And that is, there are lines that are stretched out and others that get compressed. So I think of it kind of like an earthworm that's elongating and stretching out and scrunching up to move. The idea is that as the wave front passes, the lines kind of bunch up. So this would be how a P wave moves. Another way to see it is to imagine if that ball was a stationary point in the Earth. As the wave front passed, it would move forward and back. The next kind of wave we'll discuss is a secondary wave. Secondary waves, also known as S waves, move up and down like a regular traditional ocean wave that you're familiar with seeing. You can use a simpler drawing of this diagram, or I'll show you some animations in a minute, or simply describe it in the box. They cause more damage than P waves, but they're significantly slower than P waves. They move at about half the speed. Understanding how P waves and S waves move at different speeds can help us figure out the distance to the earthquake, which becomes really important when trying to figure out where the epicenter of the earthquake is. And finally, secondary waves only move through solids. That becomes important as we try to understand the interior of the Earth. To show you how they move, once again, it's more up and down like a traditional wave would be that we would think of. To get a better idea of how a rock body or even, say, a house would behave when an S wave passed, it would look something like this blue dot as the wave went by. Again, it's mostly an up and down motion. The last type of wave we're going to discuss are surface waves. Surface waves, there's actually two different kinds. There's long waves and Raleigh waves. And the important thing to note about surface waves is that they originate at the epicenter, not on the focus, hence the surface. They travel along the surface of the Earth, not through the crust. Okay. Depending on which type of wave we're talking about, the movement varies. One moves kind of side to side, the other moves kind of rolling. I picture the side to side one like a snake, and the rolling one to move kind of like tumbleweed in the wind. I'll show you an animation just momentarily. It's important to realize that they are the most destructive. Because they're at the surface, the energy doesn't have a chance to dissipate before it gets to where the people in the buildings are. And finally, they are by far the slowest type of wave. So both the side-to-side motion and the rolling motion really create quite a lot of havoc on the surface of the Earth. That becomes quite a bit more apparent when you see how they move. This is a Raleigh wave. It moves like tumbleweed. This is a love wave, which moves more like a snake. The two usually travel together, creating quite a lot of havoc. So how do we know this stuff about earthquakes and about the waves? Well, we can detect the waves using a tool called a seismograph. A seismograph basically is a way to record the seismic waves. There are some seismographs that are very old school, which is kind of like this diagram here. So there's basically a pen hanging from a weight and a paper. This paper would move along it in a roll, kind of like a conveyor belt. And if there's no shaking of the crust, the paper's going to have a nice straight line. And when the crust starts to shake, underneath it, the weighted ball will continue to hang, but the paper underneath it will jiggle and the wave will be recorded. Now, of course, we have much more sophisticated technology with computers and sensors, but they're all based on that basic idea. And we can record on the seismograph the arrival of each type of wave. And by analyzing that, we can again learn a lot. So why do we care? Well, it can tell us two major things. The first of which is where the earthquake occurred. So we can do something called triangulation. We know the relationship between the arrival of the P waves and the S waves. We know how quickly we can expect them to arrive given what type of wave they are. And so if we find out the difference between them, we can extrapolate how far a particular seismograph reading was taken from the earthquake. We can then compare the distances from a couple of different seismograph stations to figure out where exactly the earthquake was. So we're going to do a lab with triangulation, so I won't go into much more detail than that because you'll learn it from the lab. We can also use the where different seismograph readings are taken to figure out the structure of the interior of the Earth. We'll save that for another time. As always, make sure you come see me if you have any questions.